to infinity and be no, it doesn't ring, right? All right, moving on. Previously, we explored finite limits and what happens as we approach a finite point, but today we are going to see what happens as we approach infinity with our function. From this zoomed in perspective, I mean, I know you can see that it's 1 over x here, but from this zoomed in perspective, it looks like this graph is just a straight line, like just a linear equation, right? But as you zoom out, you can start to see that this graph sort of curls, right? Well, not curl, divergence and curl is a separate thing, but it sort of curves along here, right? And as you zoom out further and further and further, you can start to see what values that this function eventually settle at, right? That's essentially what we're looking at when we evaluate a function that approaches infinity. What value does this function approach as x gets larger and larger and larger, or if x gets smaller and smaller and smaller in the case of negative infinity, right? You're not evaluating what happens as you approach a specific value. You're evaluating how this function settles, what happens to f of x, or what happens to y, or your height essentially, as you keep getting larger and larger and larger and larger values of x, or whatever variable you choose, right? As you might know already, the limit as x approaches infinity of 1 over x is 0, right? Because it keeps approaching, because this 1 over x term keeps getting smaller and smaller and smaller and smaller until it becomes negligible, right? If we have plus 1 here, it's going to end up approaching the value 1, because this 1 over x term adds on a smaller and smaller and smaller value as you get larger values of x, right? So this approaches the value of 0 right here. But if we take a look at sine x, it ends up oscillating between the values of -1 and 1 every 2 pi on the x-axis, right? So it never fully approaches a value, all right? What about x squared? As we approach x is equal to infinity, y will also approach infinity, right? Or whatever variable you choose, right? This will end up approaching infinity right here. This is the core idea of what we're trying to look at, right, in more detail in this video when we see the limit as x or some variable approaches infinity. One core concept of analyzing functions as they approach infinity is to look at the growth rate of the function itself. In the case of rational function limits, you're taking a look at the denominator, or the numerator here, and the denominator here, and seeing how their growth rates compare. In the case as x approaches infinity, any constants in this expression are going to be insignificant as x approaches larger and larger and larger values. So this plus 1 term, this plus 1 term, this plus 2 term, and the other one down there, all these constants play little relevance as these x terms get larger and larger and larger. These x terms are going to be so large that these constants are going to become insignificant, right? So it's simple, the idea that you can just ignore them and turn this into an expression like 3x over x squared. This one's more simple to analyze, but right away you can see that this growth rate of this top expression is much slower, or much less, than this bottom expression. The top expression grows linearly, whereas this numerator grows quadratically, right? So it is safe to say that this numerator is going to grow much faster. As a result, it's going to have a similar behavior to 1 over x in that it's going to approach the value 0, right? Let's take a look at this example right here. So x cubed plus 1 over x plus 2. Same idea here. These constants are going to be insignificant for larger and larger and larger values of x. It's safe to just ignore them and create a simpler expression like this to analyze. And you can see from this power right here that our numerator up here is going to have a much higher power in comparison, or a much higher degree in comparison to our denominator. So as a result, this will end up being unbounded. It'll end up approaching infinity as x approaches infinity, because it'll behave similarly to x, not x cubed. It'll behave similarly to x squared. All right, what about this bottom expression right here, this bottom limit? Right, they're both the same power, the numerator and the denominator, and they seem pretty hard to evaluate analytically, right? So why don't, unless you could wanted to divide the top expression by the bottom, but that's too much work, right? You don't need to do any of that. So I'll show you just a visual way of seeing this, right? And then I'll show you like an algebraic way of taking a look at this. So you can see that these two growth rates are the same, but these constants will play little relevance or will be insignificant for larger values of x. You can just cross them out and you get 2x squared over 5x squared. And you can simplify this. Both the bottom and the top have the same x squared growth term. So these can cancel out. And eventually, this function, or this expression right here, is going to approach the value 2 over 5 as x approaches infinity. If you wanted to solve this analytically, you already know that the limit as x approaches 0, or as x approaches infinity, of 1 over x is equal to 0. Subsequently, 1 over x squared, 1 over x cubed, as these just have higher growth rates in the denominator, right? So any of these expressions will approach value 0. So what you can do is you can multiply both the top expression and the bottom expression by whatever the highest degree term here is. And it's more interesting once you get to square roots and whatnot, but you can multiply all these terms by 1 over x squared, and you end up getting 2 plus 3 over x squared over 5 plus 3 over x squared. So these terms, as x approaches infinity, will end up approaching 0. So 0 here, 0 here. And as a result, the limit as x approaches infinity of 2x squared plus 3 over 5x squared plus 1 will end up approaching 2 over 5. All right, so we have another example here. The limit as x approaches infinity of x over the square root of x squared plus 1, right? If we take a look at this with our, just visually looking at this, seeing what it'll be, well, let's not keep that equal sign right there. You could cancel out this constant, right? As you get larger and larger values for x, this constant will play smaller and smaller and smaller role of the actual value of the function, right? So it'll just be x over square root of x squared, right? It's going to become insignificant as these values get larger and larger, which can be, this expression can be simplified to x over x, which can be simplified to 1. If we were to solve this like algebraically, I'm just going to rewrite this expression here. If we were to multiply both the numerator and the denominator by 1 over x, you can distribute this. Well, before we distribute it, we can bring it underneath this root right here. So this will become 1, and this will become 1 over x squared. 1 over, let me reduce the size of this font, or this pencil. 1 over x squared times x, I forgot to put that there, x squared plus 1, right? And if we distribute this into here and into here, I'm going to bring this whole expression down. We're going to get 1 over 1 plus 1 over x squared. We know straight away that this is going to approach 0 as x approaches infinity. So you can ignore this term again, right? And this will become 1 over the square root of 1, which will be 1. However, what do you think happens as we approach negative infinity, right? Well, for one, this value over here, this numerator right here, is always going to be negative for negative infinity, right? It's just a linear expression, right? However, if you plug in a negative value into this, you're going to still get a positive root. Well, assuming the root is positive, right? You're always going to get a positive root. So this will always be negative, this numerator will always be negative, and this denominator will always be positive. So instead of positive 1, we are going to end up approaching the value negative 1. All this talk about growth in the denominator numerator in a function might get you thinking about exponential functions or logarithmic functions and how they all play into this. As a general rule of thumb, log b of x will be less than x to the n, which will be less than a to the x, right? This is, just to be clear, this is as x approaches infinity, not for the entire domain. That is not true for the entire domain. This also is where b, n, and a are all real values, all real numbers, right? Let's do some examples down here. So the limit as x approaches infinity of natural log of x over x is going to be 0, right? Because this natural log of x term will have a much slower growth rate in comparison to this linear x term in the denominator. So eventually it'll end up approaching 0. Limit as x approaches infinity of x squared over 2 to the x. This is interesting, right? 2 to the x. You know immediately that this 2 to the x is going to grow a lot faster than this x squared over here. So this is also going to end up approaching 0. And let's do another example. Limit as x approaches infinity of 2 to the x over x to the 10th power, x to the 100th power, x to the 1000th power, 10,000th power. Doesn't matter really, but it'll still approach infinity, right? That's because this growth rate of 2 to the x over here is still higher than this x to the 10,000th beast over here. At some point in the domain of these two functions, the growth rate of 2 to the x will be able to overcome this denominator over here, and it'll end up like, well, this is your x-axis, your y-axis. It'll end up going like this, and then it'll shoot up out of nowhere, probably. I mean, you could probably graph it if you really choose to, but the point of this is to not need to graph it in order to see the limit, right? I don't think you could really graph x to the 10,000 very easily. But while these methods are very hard to solve using algebraic methods, right, you can easily just look at them and evaluate the limit by considering the growth rate of the numerator and the denominator.